Now we can look at a real-world measuring device, one we can actually physically implement. Now in the table below, we see the best we can achieve if we try to implement an operator for a measuring device that records the z-value of a qubit onto itself in a way that doesn't perturb it. It's important that the measuring device doesn't perturb what it's measuring, because if it does, then your measurement wouldn't reveal what's actually there. But in this case, the table we show at the bottom, we're not changing the ZQ value we're actually measuring. However, if you notice, we do change its XQ and YQ values. Those get changed in a way that depends upon the measuring device's X values. We can't actually account for how we perturb the qubit's X and Y values unless we knew the measuring device's X values, because the way they're perturbed depends upon the measuring device's XM values. So how could we account for this perturbation to figure out what the qubit's initial values were? Well, one thing you could imagine is that we can introduce another measuring device to measure the first measuring device's X value. Since if we know that, we can divide the qubit's new XQ and YQ values by that XM value, and we can recover the qubit's initial X values, and that will allow us to know all three of the qubit's values. But we actually run into a similar issue, where if we construct an operator for a measuring device to measure the first measuring device's X value, then we perturb its Y and Z value in a way that depends upon the new measuring device's values. But the thing is, we store the measurement result in ZM, and so if we perturb ZM, then we erase our result. So if we want to account for how we perturb that result, we would need to introduce a third measuring device to measure the second measuring device. But then we would have the same problem repeat itself, and we basically end up in an infinite regress. And so we have to conclude that it's just impossible, given the laws of physics, to construct a measuring device that actually can record all three values of a qubit. Because each measurement of one of its values always perturbs the other values in a way that depends upon the measurement results values that we also can't know, because if we try to know them, we can end up in this infinite regress. So we can only ever know one of its values at a time, and when we learn that value, we also have to keep in mind that we always perturb its other values in a way that's unpredictable. So here's what this operator that we've been talking about actually looks like. So it's quite a large operator, but what it does is the control is your least significant qubit, and that is the qubit that's being measured, and then the target is the most significant qubit, and that's the qubit that acts as the memory for the measurement device. Now this operator very specifically will use the Z observable of the target qubit as the pointer, and it will measure the Z observable of the control qubit. There are operators like this for different pointers, so one that will record the state of a qubit onto the Y observable, or Z, and there are different operators that will measure different observables. Although typically it's common not to actually use a different operator, but instead, for example, you can apply the H operator to swap the X and Z value, then use this operator to measure the Z value, and then apply the H operator again to swap the values back, so you would have effectively measured the X value. So you can technically use this operator combined with other operators to measure any of the three values of the qubit. So at the bottom right here, you have a quantum circuit, which represents an actual example of making a measurement in between the application of two H operators. So normally if you apply the H operator twice, it cancels itself out. You're just swapping X and Z twice, which two swaps returns to the same place, and you're negating Y twice, and two negations cancels itself out. However, remember that a measurement of Z perturbs X and Y, and they perturb it in a way that depends on the measuring device's X value. And since we don't know the measuring device's X value, we no longer know the X value of qubit 0, which here, qubit 0 is the qubit being measured, and qubit 1 represents the measuring device's memory state. Hence, when the second H operator swaps the X and Z values back for qubit 0, it doesn't cancel itself out, but instead we are left not knowing what the final Z value is for qubit 0, and thus we would expect a random measurement result if we tried to measure it at the end of this whole process. If we just have two H operators side by side, they cancel themselves out. But if we make a measurement between them, then they don't cancel themselves out. We get a different output where, if we did a second measurement after all three of these operators, we would get a random result at the end. You can actually see in this table where each row represents a moment in time in this process where the first line at the top represents the observables and the second line represents the expected vector at the very beginning of the process, and then the last one represents it at the very end, we can see that at the very end of the process, the IZ value, which represents qubit 0's Z value, has an expected value of 0, meaning it could be either +1 or -1 with equal probability. We don't know. So now we can actually understand why we need this expected vector to be so large. Why do we need not just ix, iy, iz and xi, yi, zi? Why do we also need these things like xx, xy, xz, yx, yy? Why do we need those things? Well, let's imagine that the CX operator isn't actually representing a measuring device. It's just representing some physical interaction that's happening between two qubits. And since it's not representing a measuring device, we don't have access to this recording, quote unquote, it makes. And so the only measurements we're doing is the measurements at the end of these two operators being applied to these two qubits. The H operator followed by the CX operator. So now let's think about what happens. Initially we know that Z0, that's the Z observable for the qubit 0, is +1, and we know that Z1 is +1. Because in quantum computing, that's just the state qubits always starting at the beginning of every program. After we apply the H operator, that's going to change our knowledge, so we know X0 is +1 and Z1 is +1. Because we're applying the H operator to qubit 0, so we're swapping X0. So now we know its X value, but not its Z value. Now the CX operator, if you remember that table, it sets Z1 to Z1 Z0, and it sets X0 to X1 X0. But there's an issue here. We neither know X0 nor X1. And so if we only kept track of the individual values for the individual qubits, there would be nothing more we could say about the system, as we will now know none of the values for any of the individual observables for the qubits. Because we don't know X0, we don't know X1, we don't know the products of them, so we don't know the Z1 and X0 value anymore. After we apply the CX operator, we don't know any of the values for any of the qubits. But that doesn't mean we can't say anything about the system, because initially we knew that Z1 equals +1, and so if we learn that Z0 is equal to +1, then it must be the case that Z1 equals +1. And if we learn that Z0 is equal to -1, then we would know that Z1 must be -1. We know this because Z1 is formed by the product of Z1 and Z0. We know that the products of Z0 and Z1 must be 1. That's to say that they're positively correlated with one another. So as you can see in the table above at the very end on the last row, we have 1 in the ZZ column. So we have 0 in the IX, IY, and IZ column, as well as the XI, YI, and ZI column, but we have values in the other columns. In this case, ZZ, we know it's 1. So if we didn't use this very large vector that keeps track of all these correlative values, we would have nothing to say about the system after we apply these two operators. We couldn't make any prediction at all, but we can make a prediction because we're keeping track of these correlations. So we can make a prediction that if we measured the X values, we would find that the products of them equals +1. If we measure the Z values, the products of them would also be +1. And if we measure the products of the Y values, they equal to -1. So we don't know the individual X values, we don't know the individual Y values, but we know the products of them. We know that the X values and the Z values are positively correlated, so they must be the same. We know that the Y values are negatively correlated, so they must be different. But we don't know anything else about the system. So again, it's important to understand this is why we use these very large vectors that grow exponentially in size, rather than just describing the expected values for the X, Y, and Z values separately. Because if we did that, we can set up a situation like this where we couldn't make any prediction at all, because we don't know any of the individual observable values. But we can still make a prediction because we keep track of the correlative values, the products of the values. So for example, I could predict, even though I don't know the Y values, their products are -1. So the outcomes for the two qubits must either be +1 and -1 for the Y values, or -1 and +1 for the Y values. They must be opposites because they're negatively correlated, so their products must be -1. Now in this slide, I'm showing how to actually use the JavaScript library I'm going to link in the description. Here I'm using it in Node.js. What I do is I first initialize 3 qubits, and you can see it creates an expected vector vector for 3 qubits. And if you look at the code for it, all it does is do the Kronecker product of 3 qubits with an expected vector where you know that z equals +1. So each of the qubits start with z equals +1. Then we evolve the expected vector by a combined operator of IIH, where I is the identity, meaning it does nothing, and H is the H operator. And if you look at the code for this, it's just doing the Kronecker product of those 3 operators. So what we're doing is we're applying the H operator to qubit 0. In the next one, we apply the I operator, which does nothing, and then this combined with the CX operator. So what that'll do is what you see in the diagram on the bottom right. We're applying the CX operator between qubit 0 and qubit 1. At the top right, you can see that continues on the code. We are combining CX with I. So we're applying the CX operator to the most significant 2 qubits, which is qubit 1 and qubit 2. And then what we do is we use this expected.observables function, which just returns the index number of an observable. Then we're looping through and we're printing out the values of observables XYY, YXY, YYX, and XXX. And as you can see, we know that the products of these values are -1, -1, -1, and +1. Now this here is actually a famous experiment called the Greenberger, Horn, and Zeilinger experiment. And the specific state we've set up where we've correlated 3 qubits together in this way is actually called a G8Z state. Finally, I want to talk about one last concept. So let's go back to how we thought about qubits as a sphere that you can measure on a different axis. So far, we've only been talking about discrete values for the expected values of -1, 0, or +1. However, there's no reason why, if you had a sphere, that you could only measure it on the x, y, and z axis. Theoretically, you could take the sphere and measure it on any angle between those 3 axes. So you can measure it, let's say, halfway between the z-axis and the y-axis. And in real life, you can do this. And when you do these kind of measurements, they're called weak measurements. A weak measurement is when you make a measurement in between the observables. And when you do this, you actually get continuous expected values. The values can change continuously rather than discretely. And the amount that can change depends on quote-unquote the strength of the measurement. So if the angle of the measurement is close to the angle of the observable we know, so if I know z equals +1, and the angle is such that it's very close to the z-axis, then there's a minor impact on the expected values. However, if we make a measurement that's very far off that angle, then there's going to be a major impact on the expected values. On this chart, we're showing the change in the expected values given a value we know. First, look at the solid line, not the dotted line. If you look at the solid line, we know that the value of this observable is +1, and then we can imagine changing the angle of the measuring device, where 0 degrees means we haven't changed it at all, so we're measuring that same axis. If we measure the exact same axis we know, and we know it to be +1, then of course we're going to measure +1. But as we change the angle, the expected value changes continuously. If you see, if we change the angle 90 degrees, we're now measuring a different observable, so we're going to get 0 for the expected value. We don't know what it is at all. And if we actually measure at an angle of 180 degrees, then that's like flipping the measuring device completely upside down, and we actually just measure the opposite of what we originally knew. So we'll measure -1. And if we measure 360 degrees, that's a full rotation, so it's back to where we started. So that'll have the impact of not rotating it at all. And then the dotted line is the case where we initially know the value to be -1, and we're looking at how the expected values change as we rotate the measuring device away from that value. So remember how we talked about every measurement device can be described by an operator. So if there are weak measurements, and every measuring device can be described by an operator, that means necessarily there must exist weak operators. So these are operators that when they act on a qubit, they change the expected values in a way that's continuous. They don't necessarily neatly just swap values around, so they might actually give you a continuous value that doesn't necessarily fit neatly into the box of +1, -1, or 0. So here I'm showing you the 3 simplest continuous operators. So these operators are defined with a value theta. So you have the rotation x, the rotation y, and the rotation z operator. And they all take some sort of an angle of rotation. No matter how you rotate the expected values of a single qubit, the square of its expected value for x, y, and z will sum to 1. So the expected values actually rotate on a unit sphere. So now we can talk about the knowledge balance principle. So no matter how we manipulate an expected vector, the sum of squares of all of the expected values can never exceed 2 to the power of n, where n is the number of qubits. So at the bottom I show that equation. We're basically just summing over the square of all the elements of the expected vector. Recall how we always have a 1 at the beginning of every expected vector that's just fixed. This number actually includes that 1, and that 1 is not useful information because it's always equal to 1. There's nothing to learn about it. It's a constant value. So actually 2 to the n minus 1 is sort of the cap on useful information you can have. And you can also recall how we mentioned that the expected values of the qubit lie on a unit sphere where x squared plus y squared plus z squared equals 1. Well, if you add that 1 for the identity observable, that fixed 1 value at the beginning of each vector, you get 2, which is 2 to the 1. And so that's the maximum amount of information we can know about a single qubit. Now, the total number of observables, and thus the size of our expected vector, because we assign an expectation value to each observable, scales by 4 to the n. Now, due to complementarity, gaining information about the system causes us to lose information about other parts of the system due to disturbing it. And this means we cannot exceed this total knowledge bound of 2 to the n. If we're at the bound, meaning that we know information equivalent to 2 to the n, that's the summation of all the knowledge we have, it's equal exactly to 2 to the n, and then we make a measurement to gain more knowledge about the system, then that means necessarily knowledge must be lost elsewhere. Some knowledge must be lost to balance out the knowledge we just gained. And that knowledge is lost because we perturb a part of the system that we can't account for. Now I want to leave you on something to think about. If the total knowledge we can have is limited to 2 to the n, but the size of the expected vector grows at a rate of 4 to the n, then it'll typically have many zeros in it, and therefore have a lot of redundancies. If it has so much redundancy, that could potentially allow for a more compressed notation that can serve the same purpose but with a much smaller vector. If this notation compressed all the information down in a way that was lossless, so we didn't lose any information, then the optimal compressed form would scale by 2 to the n, because that's the same rate in which the total knowledge we can have about this system scales. Can you take a guess on which you think that compressed notation is? I'll leave that as an exercise to the viewer.